Hi guys, so today we'll be doing question number 4 of the AP Calc 2011 AP questions that are on Mr. Farrar's website. So the question basically says the continuous function f here is defined on the interval -4 is less than or equal to x, which is less than or equal to 3. And the graph consists of 2 quarter circles and 1 line segment. And I kind of drew on it, but if you have the question yourself, you can see the graph a little clearer. And it gives us this. It says let g of x equal 2x plus integral 0 to x f of t dt. And we'll start with part A. It says find g of -3. And it asks for a couple more things, but we'll get to that later. So to find g of -3, we basically plug in -3 to the equation that they've given us. So we'll do -3 times 2 plus 0 to -3 are our limits, f of t dt, and that's obviously 6 plus, and for this part it's basically saying that we have to find the area under the curve in this graph from 0 to -3. So we'll take this 0 to -3 encompasses this thing here, which is happens to be a quarter circle, fortunately for us, so we can find that area pretty easily. We'll just say area equals pi r squared. R squared is 3 times 3, that's 9, since our radius is 3. And we divide that by 4 since it's a quarter circle. So we get -6, and then there's this thing. And you'll notice that this limit is greater than the upper limit, which doesn't make sense. And we can actually fix this by making this whole thing negative, which would actually flip the integral limits. So we would make that a -9 pi over 4. And basically we get that our answer is -6 minus 9 pi over 4. And that's the first part for part A. So next it asks us to find the g of x, g prime of x. So we basically have to derive this. And g prime of x equals 2 plus just f of x, because if you try to derive an antiderivative like this, or an integral, then you just get the normal function. So we get 2 plus f of x. And yeah, that's g of x right there, that's the second part. And thirdly, we have to just find g prime of -3. So we'll just plug -3 into that, and we get 2 plus f of -3. -3 happens to be a 0. I've already kind of circled it when I was working on it earlier. And that just gives us an answer of 2. So that's it for part A. And we'll move on to part B now. It says determine the x-coordinate of the point at which g has an absolute maximum on the interval from earlier -4 to 3. And we have to justify our answer. So in order to do this, we have to take critical numbers, which is a great way for finding extrema, because you have to do test values with them and stuff. They're real points of interest. So in order to find these critical numbers, we have to take our derivative and basically set it equal to 0. So when this equals 0, the only way for this side to equal 0 is if f of x equals -2. -2 plus 2 is 0. And then, so in order to find out when this equals -2, well, we can kind of get an idea of how to find that if we look at our graph, because the only part where it's going to be -2 visibly is in this area here. So, and that's part of this line. So we can do that, we'll find this line equation. They give us 2 points. We get 3, -3, and 0, 3. And then we find the slope in between. You get 3 minus 3 is a 6, and you get 0 minus 3 is a negative 3, and you get a slope of negative 2. And then we plug it into point slope, you do some number crunching, you basically get that your answer is negative 2x plus 3. And when does this thing equal negative 2? It comes out to be x equals 5/2 with some real simple algebra, y equals mx plus b. And so that's your critical number there. This is a point of interest. And then you put that in with your test values in this little chart thing that we have done many times. 3. And so we'll just find values in between. 0 is a great one here. We could do 13/5 here, because this is 2.5. 13/5, that's 2.6, so it's in between. And then we basically plug these test values into our derivative g prime of x to look at the behaviors of the slope as it goes throughout the graph. And so g prime of x at 0 would be 2 plus f prime, or f of 0, which comes out to be 3. So that would just be a positive. And then for 13/5, we can kind of see that it would be, since it's 2.6, it would be around here. It would be slightly greater than 2. The magnitude would be slightly greater than 2. So it would actually come out to be slightly negative. And that means that our slope's increasing, decreasing for g, the graph of g. So that makes our answer that there is a maximum indeed at, there's a maximum at 5/2, x equals 5/2, because g prime of x goes from positive to negative. And that's a sufficient response right there. And we can do like a therefore. Alrighty, now on to part C. It's saying find all of values of x on the interval for which the graph g has a point of inflection. So this is basically like part B, but we're just working in the second derivative. So we'll find that second derivative. G prime of x equals, this cancels, it's just done with, and then we get f of x, technically that's times 1, it doesn't really matter. And then we have to find where there's a point of inflection for this, so we'll get a critical number for here. We can see that g prime of x changes like exactly as f prime of x changes, so it works like in sync with our first derivative. So we can just find when, in order to find when our second derivative goes from plus to minus, or minus to plus, we just find when the first derivative goes from plus to minus or minus to plus. And this is real easy because you can actually just look at the graph and see it. You know, here it goes from plus to minus, and that's really like the biggest slope behavior on the graph, so our point of inflection is actually right here where x equals 0. So therefore there's a point of inflection at x equals 0 because g prime of x changes from plus to minus, and that's just directly with the first derivative changing our slope of the actual graph. All right, now we can move on to part D. So it says find the average rate of change of f on an interval, and it also says that there's no point C on the graph for which f prime of C is equal to that average rate of change. So the average rate of change that we calculate, there's no slope on the graph that equals that at any point. And we have to explain why that doesn't contradict our good old mean value theorem. So we'll just start with the first part. You find the average rate of change. Our average rate of change formula is you find your f of your bigger x minus f of your little x over bigger x minus little x. And in this case, that would be f, our bigger x happens to be a 3. It's kind of hard to see. Minus our little x, which happens to be a -4. And then we just do that subtraction on the bottom. You get 3 minus 4. So we know we have a 7 on the bottom. And then we just look at our y values for these, and we have a -1 for the -4, and we have a -3 for the 3. -3 minus -1, that's -3 plus 1, that's -2. -2/7 is our average rate of change for the graph. And it tells us that there's no c value on the whole graph that would equal that rate of change. So we have to explain why that doesn't contradict our mean value theorem. And the mean value theorem states that in order for it to work, our graph must be differentiable. Here, I'll write this down. Our graph must be differentiable at all points within the interval. But if you look at this graph, you can see that it is not differentiable within all points of the integral. First, there's the interval. First, there's this one here at -4, where the slope is actually none. There's no slope because it's vertical. And then here at 0, our point of inflection, the slope is indeterminate because it kind of just goes down all of a sudden. You can't determine a slope at that point. It could be anything. So it says it has to be differentiable with all points within the interval, but our graph f isn't at -3 and 0 because no slope and indeterminate slope, respectively. And yeah, that's it for our problem. That's the explanation for part D, and that's about it for today. If you want to find more problems like this, you can go to section 5.3. It's really great. You know, the first few problems in that section are just like this. They have multiple parts, a lot of the same questions they're being asked. Yeah, it's good extra practice. And yeah, that's all for now. Thank you.